a SmartNIC environment or platform using chiplets. Okay, Cliff talked about an open economy. I might use the term ecosystem, but please treat that as the same. The other thing, DJ mentioned SmartNICs. So I'm gratified that I think I'm going to bring home all of that in terms of how it comes together in a real system in my talk. So I'm from Apex Semiconductors, and I lead the advanced packaging and systems for Apex. Jawad showed you some examples of chiplet-based SIPs that are already in production. I wanted to show you more examples here and also draw your attention to something that is, these systems have been around for almost a decade. But two main things about all of these systems, I think Jawad mentioned it, but I want to reiterate. All of these are developed, these chiplet-based systems are developed in a closed ecosystem. And the second part is the chiplets talk to each other through a proprietary interconnect. So the question then becomes, how to build a system of chiplets outside of these large vertically integrated companies and do that today. So I'm hoping by the end of this talk, I would have given you a good answer to this. So the ecosystem I'm talking about, which is probably a microsystem, is Dreambig and Ventana are the chiplet vendors. They've done the front-end architecture and the software and platforms around it. Blue Cheetah provided the die-to-die Bow Phi. And then Apex, the company I work for, translated those front-end architectures into silicon and then integrated it into a SIP. And I'll show you how all that looks in a little bit. And of course, we worked with TSMC and our OSAT partners to put all this together. The other thing you need as part of all of this is you need tools. So this is a chart that was supplied by Cadence. We have used Cadence tools for not only developing the chiplet, but also for putting together the substrate and do some of the system planning and simulations. The third important piece is, as DJ said, you need system use cases. And we're going to look at specifically a SmartNIC platform. So what are the components that make up the SmartNIC platform? So there is a SmartNIC hub chiplet, which has two die-to-die ports. Each of these ports is 1 terabits of bidirectional bandwidth. And then there's 2 by 16 PCI Gen 5 port that can also speak CXL. And then for the networking part, you have 800 gigabits of bandwidth going out to the network. The other chiplet on here is the RISC-V chiplet from compute chiplet from Ventana Microsystems, and it also has a die-to-die port with 1 terabit bandwidth to match what's on the SmartNIC hub. And there's all the each of them has 8 cores in this configuration, and there's software stack and all the reference firmware and drivers that go along with this. So some people have talked about, I'm sounding like Trump, but basically SIP is the new motherboard. So if that's true, then I'm going to argue that the chiplet hub is the queen of the SIP. And in the next slide, you will see why that might be the case. So the DMOS chiplet hub from DreamBig can be configured depending on the types of chiplets you attach to it for applications spanning anything from edge to the cloud. You can put multiple chiplets hubs together and then attach different configurations of chiplets. So it's very composable, so you can create very sophisticated systems. The processors and accelerators that you can attach to them are agnostic of the hub chiplet architecture itself, and they can be full or I/O coherent. Depending on the bandwidth required for the processors and accelerators, you can scale the I/O and memory bandwidth to match what the processor demands. And the chiplets talk to the hub, very similar to what the Fabian mentioned from Fraunhofer, that they use standard AMBA protocols between the chiplet and the hub and the other chiplets. I'm not going to say a lot about the compute chiplet other than Ventana has published some benchmarks which show that their chiplet exceeds the performance of all the incumbent chiplets, processors out there from either Intel or AMD or even the ARM, from ARM. So I don't know how familiar everybody is with the Bose standard, but what we are using here is it's a 16-bit parallel interface. Each is running at 16 gigabits. And then in this implementation, the bump pitch is 130 microns. The rest are standard KPIs that are part of the Bose standard. Typical usage of the Bose PHY, obviously you need the PHY to be the same, but the upper layers, including the link and the protocol layers, have to match for them to interoperate. So how did it all come together? Here's a top view of the package. In the middle is the hub chiplet. And then on the top and bottom are the 2 compute chiplets. The boxes in yellow or green here are the die-to-die interface. It's about, so because it's 2 slices, the length of the longer slice is about 2.6 millimeters. These are the PCI Gen 5 traces, and over here is the 112 gigabit Ethernet lanes. You can see on the bottom side of we put caps on the bottom side to help with the PDN and make sure it can meet the performance requirements. This is some detailed analysis or signal integrity analysis of the BOW interface, and we've looked at insertion loss, return loss, crosstalk, and given the short distance, and we've done some things to mitigate crosstalk, and everything looks really good. So we've talked about, I think Jawad mentioned, there's a lot of shift left that needs to happen because chiplet designs are more complex than a traditional SoC. So we have had to look at, obviously, PDN, but we've looked at warpage. We had to work with the vendor to create a DOE plan so that we could fine-tune the assembly recipe, because the way we place the chiplet kind of violates their design rules. But because we wanted to make sure that more than one vendor can manufacture this, we had to combine design rules from two OSATs and make sure the design worked. And then we also did the thermals to make sure we got the right lid and TIM and all that selected for this. Yogan talked a lot about the test strategy. I'm just going to say we're going to do KGD through wafer probing, and then for final test after assembly, we have some DFT structures, and in case we have any issues, because this is kind of greenfield for us, we also have ways to directly test each die individually through BGA access. Obviously, the die-to-die is new, but we're hoping to learn, and maybe I'll share what we've learned in another forum. Okay, all of this slot is where the package SIP goes in, and then you have the PCI. This is the Ethernet QSFP, and then on the north side, we have options to either connect a M.2 card, or there's another PCI connector to do other kinds of add-in cards. Okay, DJ talked a lot about composable, scalable, flexible architectures. So what the chiplet hub architecture allows us to do is, in what I showed you earlier, it has two die-to-die slots, but that can be easily extended to multiple die-to-die slots. You can add memory, and basically you can add as many CPU compute chiplets as you need, and that gives you the scalability. Also, you can mix and match different types of chiplets, any type of DSA compute, and that way you get a very composable, extensible system. Literally what it does is, what kind of system you want to build, you can delay that decision until late. So main point here is to Cliff's idea of an economy. Right now we've seeded this with two chiplets, a hub and a compute chiplet, other things like a 5G chiplet, and then AI, and there are many others in the works that will complement these, and then you get start. You can already see, given that uh, the intent of Dream Big, I think, is to be open. So anybody who has some value-added chiplets for a particular system use case or market uh, will be able to attach their chiplet to this hub. So hopefully, with the presentation, I've been able to answer the question of, can we do a SIP, chiplet-based SIP outside of the big vertically integrated companies? And I think the answer is yes. What I've shown you is a simple but powerful 3-chiplet SmartNIC platform built on low-cost organic substrate. And more importantly, the general architecture of the Dream Big chiplet hub makes it very scalable and extensible. I do want to highlight that the bow, having the bow open standard, die-to-die interconnect standard, is a key enabler to make such a system possible. And Blue Cheetah tells us that they have silicon-proven IP, and which we've already integrated into this platform. If you want to learn more about all of this, I've put links here to the ecosystem partners. You can learn more and reach out to any one of us. I'm just going to mention, people have already mentioned this, but there are a lot of work streams within the ODSA. If you have ideas and you want to collaborate, you're welcome to do so. Thank you.
Well, next we have Walter, actually from a fairly new company, which has, in my mind, a very interesting technology.